All right, let's just dive right into this explainer and look at how we can architect robust AI applications using AWS vector databases. Look, if you're building generative AI right now, you already know the deal. Foundation models are absolutely incredible, but they have this massive blind spot. They only know what they were trained on. To fix that, we literally have to build them a brain, a persistent memory. And that's exactly what we're going to master today by breaking down some core AWS architectural guidance alongside some really cutting-edge academic research. So here is our blueprint for today. We'll be covering the language of AI, building RAG architectures, choosing your AWS database, the metadata filtering challenge, and finally, costs and takeaways. Let's get to it. Starting off with Section 1, the language of AI, translating raw data into machine understanding. Okay, so here's the literal million-dollar question for any developer right now. How do you give an LLM long-term memory? Because by default, large language models are stateless. They don't know your enterprise data, your customer records, none of that. To give them that context, we have to feed them the right information at the exact moment they need it. But how do we store that info so the AI actually understands it? Well, traditional SQL databases, yeah, they just can't handle this. A standard database looks for exact keyword matches, but AI needs to understand context and semantic meaning. So we need a system optimized for multi-dimensional similarity search. And that right there is what a vector database does. It doesn't just look for the word bank and get confused between a financial institution and a riverbank. It looks at the mathematical proximity of actual concepts. It's actually pretty brilliant how this embedding process works. You take raw data, text documents, PDFs, images, whatever's sitting in your Amazon S3 bucket, and you pass it through an embedding model. That model transforms your human-readable content into arrays of numbers, vectors. Each document becomes a specific coordinate in this massive, continuous, multidimensional space. So words or concepts with similar meanings, they're literally mapped closer together in that space. Which brings us to Section 2, building RAG architectures, connecting the pieces. Now this is where the magic happens, the classic retrieval-augmented generation, or RAG loop. You can see how the content flows into the embedding model, becomes a vector, and lands right in the vector database. When your app needs an answer, it doesn't just blindly ask the LLM. No way. It queries the vector database first, retrieves the mathematically nearest, most relevant context, and hands that highly specific data over to the foundation model. The result? An accurate, hallucination-free response. But as simple as that loop seems, the infrastructure underneath it is absolutely critical. If you get this architecture wrong, you're going to hit massive bottlenecks that can totally cripple your app's performance. Pick the wrong database, and you get poor query latency, meaning your users are just sitting there waiting. You might hit scalability walls as your vector account explodes, struggle with data ingestion, or, and this is a big one, fail entirely when your users try to apply complex metadata filters to their searches. To avoid those nightmares, AWS gives us a lot of options. Let's move to Section 3, choosing your AWS database, the architectural menu. Let's break down this spectrum of performance and cost. If you're building, say, a real-time recommendation engine, and you need blistering, ultra-low latency, Amazon MemoryDB is your go-to. It gives you sub-millisecond latency because everything is in memory. But on the complete opposite end, if you're prioritizing storage economics for billions of vectors, maybe for an archival RAG app where sub-100 millisecond latency is totally fine, then Amazon S3 Vectors is the move. And sitting nicely in the middle, you've got OpenSearch and DocumentDB for high-frequency or MongoDB-compatible workloads. And the menu just keeps going. For those of you mixing traditional relational queries with AI, you'll probably lean toward Amazon RDS with the PG vector extension. It's awesome because you keep your standard SQL tables, but just add vector similarity search right alongside them. Or, if you're building complex knowledge graphs, think fraud detection networks, Neptune Analytics enables Graph RAG, so you can traverse complex relationships while doing your vector search. And for pure out-of-the-box enterprise search, Amazon Kendra has you covered. All these options really build up to one massive architectural decision. Do you want to build and manage this whole pipeline yourself, or do you want to let Amazon Bedrock handle the heavy lifting? Individual databases give you total control over the retrieval logic, which is fantastic for specialized engineering teams. But managed Bedrock knowledge bases, that's a fully managed service. It automatically handles data ingestion, chunking, vectorization, the whole shebang. If you just want to focus on the application layer, Bedrock is a huge accelerator. But there's always a catch, right? Section 4, the metadata filtering challenge, the plot twist. This quote from recent UC Merced research is a bit of a harsh reality check. Semantic similarity alone is rarely sufficient for context retrieval. Basically, just finding similar text isn't enough in the real world. Imagine a user searching a legal database for intellectual property disputes. Easy, right? But wait, they only want cases from the state of New York and filed in 2023. The database can easily find the semantic match for IP, but honoring those strict date and location filters while navigating a continuous mathematical space, that is incredibly tricky. Enter FANS, or Filtered Approximate Nearest Neighbor Search. This is that exact complex challenge of making your database honor strict structural filters while traversing high-dimensional graphs. You're basically asking the database to do two completely different types of math at the exact same time: a fuzzy conceptual similarity search and a strict Boolean yes or no metadata filter. The academic research on how databases actually handle FANS under the hood is wild. For instance, research has found that pgvector sometimes outsmarts itself. Its cost-based optimizer frequently chooses a fuzzy approximate scan when a simple, exact sequential scan would have given perfect recall at the exact same speed. Meanwhile, systems like Milvus achieve great stability using a dynamic hybrid approach. And get this, older partition-based index types like IVF-flat actually beat the super popular modern HNSW graph indexes when your queries require heavy filtering. Who knew? Because evaluating this stuff is so hard, the researchers created a new metric, Global Local Selectivity, or GLS. GLS helps engineers mathematically quantify the relationship between metadata filters and vector neighborhoods. So basically, it's a tool to help you decide with actual mathematical certainty which filtering strategy and index type to deploy for your specific dataset. So you aren't just guessing in the dark. Let's wrap up this architectural journey and look at the bottom line. Section 5, Costs and Final Takeaways, bringing it all together. At the end of the day, you have to balance the checkbook. Architecture is all about trade-offs. Amazon S3 vectors can cut your vector storage costs by up to 90% compared to specialized databases, but you got to be able to tolerate slight delays in retrieval. On the flip side, Amazon MemoryDB demands a premium price tag, but it delivers absolute, instant recall for real-time apps. You're basically paying for exactly where your application needs to sit on this cost-latency curve. So how do we actually put this into practice? Before you write a single line of code, follow these steps. First, honestly evaluate your latency and scale needs. Seriously, don't pay for MemoryDB if S3 will do the job. Second, test Bedrock knowledge bases to see if you can just skip building the pipeline entirely. Third, and this is crucial based on that FANUS research we talked about, prototype your app and run queries with heavy metadata filters. See how the database handles them. And finally, plan your production deployment knowing your true costs. Ultimately, the database architecture you choose is going to define your AI's capabilities, its speed, and its cost. It's not just about storing data. It's about building a brain that can remember, filter, and recall information exactly when it matters most. Which leaves you with this vital question to answer for your own builds. Are you prioritizing raw speed or the smartest, most accurate filtering for your AI? Definitely something to think about as you design your next RAG system.